The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
Hello, today I am together with Thomas Jam Pedersen, who is the co-founder of Copenhagen Atomics. Hi, Tom.
Hi.
Hello, so happy to have you in here. So Thomas, right now you're a successful businessman, being the co-founder of one of the startups in nuclear. You're passionate about nuclear topics, and however, you're living in one of the profoundly skeptical countries in terms of nuclear. It sounds like a pretty hardcore set. Actually, what I could see from your bio, you are not a nuclear specialist. You're rather a software specialist. So how did it start with your career? Where did you study? What was your early career?
Yeah, so it's true. I'm an engineer, and I've worked most of my life in sort of software engineering and mathematical modeling. And then actually around the time that I learned about Thorium energy, the first time I was working as a consultant for a big energy company, a utility company, doing simulations of their energy feeds. Anyways, I've always been interested in energy because energy is such a big part of what we humans do. Like all products are made using energy, and everything we invent and everything we do is dependent on having access to energy. And that's also why the population of the world exploded when we got lots of energy from coal and oil and so on early on. Anyway, so yeah, so I'm not I don't have a degree in nuclear engineering per se, but of course I've had a lot of experience with physics and things, so it was easy for me to pick that up. And we early on I met with the other people in Copenhagen that had a background in chemistry and nuclear physics, and as you might know, a molten reactor is very dependent on corrosion and clean salts and things like that. And I also had a background in manufacturing company with stainless steel, sort of mechanical engineering. So we were a good fit, those four co-founders, when we met.
Great. Actually, what I normally see among my friends is nuclear people running away to IT fields, not the other way around. So it's
Yes.
interesting. How did it come to you? When was this moment when you said, okay, let's focus on nuclear in my career, rather than pursuing this software, this IT topics?
Yeah, so throughout my career, I've been part of several startup companies that did sort of high-tech stuff. I've also worked for Google in the past, or with Google. Anyways, and for me, I like to explore new topics, and I'm very interested in new technology that can transform the way society develops. And when I heard about Thorium energy, I was just, I didn't think that I would go into nuclear. I was just very intrigued, how does this work? And in the beginning, I was sort of just studying it to understand for myself, like, why we're not using it? Is this the next big thing out there, and so on? And then I got to know more and more, and I got more and more interested. I started going to conferences around the world where people talked about molten reactors and thorium energy and things like that. And at some point, I got a very good network with people around the world, especially in the US and Canada, who are working on these things. And I got chances to ask them all my questions. And I found in the end that I had a fairly good understanding of how everything worked. Sometimes maybe even better understanding than some of those people. But I've also spent a lot of time on it. So you could say I've sort of taken a whole nuclear degree on my own. And that's one of the things that is really great today is that, you know, back in the day when I went to university, you had to read all the books and stuff, but nowadays you can follow like a whole course of nuclear engineering at MIT OpenCourseWare or something like that, which is very helpful. And it is especially helpful if there's some specific topic you're searching for. Then, you know, you don't have to like take a whole course. You can just take those 2 classes that talk about exactly what you're fiddling with right now. So I've done that a lot.
That's really interesting because it shows that you don't need to be a specialist to be pro-nuclear, or that you do not need to have much money to get enough knowledge to become actually a professionalist, which makes me wonder what is happening with our societies right now in countries like Denmark, who even managed to implement a law that is anti-nuclear, that forbids the building the nuclear. Is it? Do you think the access to knowledge about these topics is limited, or people are just not interested, or people have their own agenda already built that they do not listen to the facts? In Denmark in general.
Yeah, I mean, Denmark, I think a little bit a special case because the position of Denmark is very good for wind power, and from very early on, like for the last 40 years, we've been building a lot of wind energy, and that's also part of the reason why the Danish Parliament chose not to invest in nuclear, which I had hoped they would do. But I mean, it's not like we are lacking energy here, and we are in a perfect position because we're right next to Sweden and Norway, where we can use those countries for storage, but there's links to their energy grids, and Sweden has a lot of nuclear power, and actually the statistics show that the Danish grid have 13% of nuclear power because we get it from Sweden. So I mean, it's a more complex story. But back to the question about sort of the democracy or like democratization of information. I really think now there's suddenly roughly 20 startups doing small modular reactors or some sort of nuclear, and I don't think that was possible 30 years ago. I really think that's because of the internet that has become possible, because now you can find all this information. You need much less resources to build something and study these a little bit more exotic or complex topics. I used to also to work in a company many years ago where we would design PCBs or print cards for computers. And I mean, the amount of resources you need to design such a card, and you had to go to libraries to find the information and look it up in big books. Now everything is just one click away, and Google is very efficient in helping you find it. So today, I mean, one guy can do the same amount of work as what it took 10 or 20 people back then to do. And I think the same is true for nuclear, because it's such a complex topic. And I mean, you cannot know everything in your head. You have to look it up. And when that time it takes to look things up is 10 times faster or 20 times faster, and our simulation tools are much better today than they were in the past. I think this is what enabled actually that we can have startup companies that wants to build nuclear, because, you know, 30, 40 years ago, it was sort of a thing that only big countries could do.
Yeah, that's amazing. And actually, Denmark has not one, but several startups. There is Copenhagen Atomics, there is Seaborg, also in Copenhagen. Yes. How do you feel the Danish people approach nuclear? Like when you talk to your neighbors, when you, I don't know, when you have some meetings with your private friends, acquaintances, do they really understand what you're doing and support it? Or do you need to explain yourself and you're a party pooper every time?
No, well, not everybody understands, but I guess that's the same in the US. I've lived there quite a bit of my life in the US. Of course, when you meet with people who are working in the energy space, or especially if you work with people who are engineers and interested in energy related topics, they usually know, and they're very interested and they want to know more. But you're also right that if you're at a family union or something, and some of those people who do not have interest in energy or interest in nuclear or engineering in general, they don't really know what it's about, and they don't really understand it. But I mean, there's many topics in society that not everybody understands, so that's okay. in relations to Denmark. I mean, I know that if you're from the US, you sort of think of the US as your primary market. But because Denmark is such a small country, we are only 6 million people. We wouldn't think of Denmark as our primary market for this technology. So I think that gave us a little bit different outlook. And also right now, Europe is sort of in a terrible state with everything is declining, not everything, but there's at least there's no growth in Europe. And that means that we don't need to build new power plants or anything. And you know quite well that in Germany, for example, they're shutting down power plants, also in other places. So even Europe is not a great market for us. And therefore, we looked around the world and look at where are the needs for energy really big. And of course, Asia is by far the biggest market for energy installation. It's actually, if you look at all new energy power plants being built, more than 90% of those are being built in Asia today. So that's sort of the main driver of the market. And of course, we're eager to see if we can supply our technology to those markets out there.
Yeah, so you told me a lot about your market right now, but maybe before we go deeper into it, I think you need to pitch a reactor. What is it about? What is the main point of this being designed and not using the other reactors that are already available on the market or thought of before? Please tell us.
Yes. Well, we are 4 founders that started Copenhagen Atomics, and when we got together and started thinking about how would we start a company and build a reactor, we agreed that it would be great if we could make a technology that could be a true alternative to fossil fuels. And you might know already today, 5% of global energy comes from nuclear energy. And we thought that, yeah, we can go ahead and build light water reactors, but I mean, a startup company doesn't really want to build light water reactors when you're in competition with even companies like Korea and Russia and China, whatnot, US brands and so on. And then we said, okay, if this is going to change the world, not just a little bit, but significantly change the world, then we need to find a way to mass manufacture nuclear power plants. And of course, we look towards France, where they have built many power plants of the same design. We also look towards what Korea is doing now in the Emirates, where they're building 4 copies of the same plant. And we said, but I mean, that's not enough. I mean, in order to sort of push fossil fuels out of the picture in the next 100 years, we need to build not thousands of reactors, but millions of reactors. It's really on that scale if we want to sort of eliminate fossil fuels. And when you start to think about it that way, like how can you build 1 million reactors? The model that is used in France, for example, okay, that was in the 70s, but still, it's not viable, right? So you must manufacture this on an assembly line. And the problem with light water reactors is that all that pressure and all those, the high pressure sort of makes it difficult to make it on an assembly line. And it sort of drives the size of those big buildings and 1 gigawatt power plants and so on. But we realized quite quickly that if you use molten reactors, you get some great benefits because you don't have the pressure. So you can build it much smaller and it requires less steel and so on. But also when you have molten salts, you can actually remove the fission products from the reactor or from the core while the reactor is running. And that means you get much better neutron economy and therefore much better efficiency out of your fuel. So suddenly things become much better, not just like 20% better or 50% better than light water reactor. It becomes an order of magnitude better. And that's really what we're shooting for, because I mean, to be honest, the nuclear energy, if we want to grab sort of the main market for energy installation in the future, we need to get the price down by almost a factor of 10. And we also need to get the time it takes to build the reactors up by a factor of 100 or even more. So that was sort of what we were looking for. In the beginning, we were just discussing, would that be possible? And I truly believe that it is possible with molten reactors. And one of the other things that we've done in Copenhagen Atomics is that we said we want to try the Thorium fuel cycle. And the reason we want to do that is because we humans have built lots of reactors in the past, more than 400 commercial reactors, but all of those were thermal reactors. There's been there's been a lot of money invested in fast reactors, but none of the fast reactors has become a big commercial success. And I believe it's because fast reactors are much harder to build than thermal reactors. And it's not as hard as fusion, but it's sort of halfway towards fusion in terms of difficulty. And if I'm going to invest my own money, I don't want to like take that risk of trying to develop something that other people have already spent 20 billion or more trying to do, and they have not been super successful. So from the beginning, we said it's got to be a thermal reactor, and the only way you can make really, really good neutron economy in a thermal reactor is if you use thorium, because with the thorium fuel cycle and thermal spectrum, you can have a breeder reactor, and that changes everything. You cannot have a breeder reactor, or at least you cannot have a breeder reactor with good doubling times if you were to build sort of a solid fuel reactor. You really need to remove those fission products in order to have super good neutron economy. So, but when we put those things together, molten reactor, remove fission products, no pressure, that means small, it's possible to make it on an assembly line, and then you can have a super good neutron economy. We thought that's the reactor that can scale, and we can build thousands of these or even more. So that was sort of the starting point. And then we quickly realized that in order for nuclear to gain some popularity again in the world, we sort of have to do something about the cost, the time it takes to build, and something about the waste, because a lot of people are worried about the waste, even though it's a little bit of a communication problem. But anyways, we thought it would be great if we could take that fuel from spent nuclear fuel in classical reactors and burn it one more time and get even more energy out of it. And that's what we try to do with our Copenhagen Atomics waste burner, which is essentially taking all the long-lived actinides from spent nuclear fuel and extracting that chemically and put it into a thorium salt, and then we can use that long-lived actinides, or especially the plutonium in there, as kickstarter fuel to get the process up and running. And then once it starts converting the thorium to uranium-233, we actually get a positive feedback, and we can sort of burn the majority of those actinides out of the salt and end up with fission products, which has a half-life of only, or not a half-life, but it needs to be stored for 300 years. So that we thought was a unique way to sort of show the public, or the general public, that they shouldn't worry that much about nuclear waste. It's not that big of a problem, and we can remove most of it in these type of reactors while producing even more energy. And of course, when we came around to the business model and sort of how can we make money, it seems that we can get paid to take that spent nuclear fuel from countries, and then we can process that or license our way of processing that to those countries and help them reduce their waste problem. So not only do we make money from the electricity we make in the end, but we also make money by removing the spent nuclear fuel problem for some countries. And you might know that there are several countries who already have billions of dollars in the bank to solve that problem. So that's what we are pursuing.
That's great. I can almost imagine you being like a service company. You have this reactor somewhere in the corner and advertising to countries like, we can take your waste and make electricity out of this, and what is the best for you? You just magically remove the waste from your country, which would be an amazing argument for all the antis, as you mentioned it already, where the first question is, what about the waste? Before anything else is asked about the characteristics of electricity production, of nuclear and so on, the first question is always, what about the waste? Can you imagine this kind of business model, like really being the service company for different countries?
Yeah, that's exactly what we want to do. I don't think it's that simple that you just drive a garbage truck over there and pick it up. but it's definitely, we want to make agreements with countries that have spent nuclear fuel and help them solve that problem in collaboration with them. I believe that their national lab will also be involved, and it's not like super simple, but of course that's the way we like to explain it to the public. But anyways, it's never simple to make, either if you want to do uranium mining and enrichment and make nuclear fuel, like no matter what you want to do, it's complex. So of course, this is also sort of complex.
Yeah, so talking about the fuel cycle, maybe it would be interesting to share a little bit with our listeners and watchers about some details of the thorium cycle. Maybe not everybody is aware of this. Could you explain a little bit how come that we can make electricity, energy out of thorium by replacing this, what we normally know that it should be uranium?
Yes. Yeah. So, I mean, uranium-235, you can get that out of the ground and you can burn it right away. It can initiate a fission reaction or a chain reaction on its own. So that's simple, and that's of course where we started as humans. But there are two other isotopes that can sustain a chain reaction. One is plutonium-239, which is not available in nature. And the other one is uranium-233, which is also not available in nature. And in order to make those two work, the plutonium and uranium-233, you need to take an element that is in nature, and then you need to sort of upgrade it to one of these isotopes. And for plutonium, you take the uranium-238, and you allow the uranium to capture a neutron, and then through a cycle, it turns into plutonium eventually. And then the plutonium will fission and fission in a way where you get extra neutrons, so that you can use those extra neutrons to upgrade the next uranium-238 atom. It's the same with thorium. Thorium is found in nature, and it's actually the great thing about thorium is that it comes out of the ground when we do mining, and we already get so much thorium out of the ground when we mine for other materials that it would be enough to power the entire world with all its electricity just from the mines that we are already doing today. So we don't even need to open new mines. So I think that's really great. And it also shows that that's the reason why the thorium is never going to be very expensive. And we also know that there's enough thorium on this planet for thousands of years of energy production. So we won't run out of it anytime soon. Anyways, back to so you take that uranium out of the ground, and then you put it in your reactor, and then the thorium out of the ground, put it in your reactor, and it's upgraded to uranium-233 by capturing the neutron and some decays, and then it's uranium-233. And uranium-233 is actually capable of doing a breeder cycle in thermal spectrum, whereas uranium-238 is not able to do that. So that's really great because, we humans, we started building reactors back in the 1940s, and already the very first reactor, I mean, the physicists back then, they were pretty smart, but they didn't have computer simulations, and they didn't know half of the physics that goes into running a nuclear reactor. But still, I mean, they were able to build it, and when they turned it on, it worked right away. It's like a sort of amazing. When we look at how difficult it was to just get the first fast reactor running, it's amazing how simple and easy it is to build a thermal spectrum reactor. And of course, this is the same here. So now you can actually take a fuel that is plentiful, thorium, and you can make a breeder cycle in thermal spectrum. And then, well, that's only possible if you have a molten salt reactor, because you need to remove the fission products from the core while you're running. Otherwise, it won't be able to breed. And if you want to make a really nice breeder that has a doubling time of 10 years or 20 years, I mean, that's the time it takes to double the amount of fissile inventory, then you really need to have a great neutron economy. And that's going to be difficult. But I believe over a decade or maybe several decades, that will be possible. And that's at least what we're shooting for in Copenhagen Atomics. But then when you do that, you have to think about how to manage all those neutrons and try to lose as few of them as possible. And that's also the reason why we're using heavy water in our reactor design. And that's a little bit untraditional, I would say. Most people who are talking about molten salt reactors, they want to use graphite as the moderator, or even use fast reactors with molten salt. But the problem, as we see it with graphite, is that after you've run it can only sit in the reactor core for some years, let's say 5 years or 7 years or even 10 years. Then it starts to swell so much that you cannot use it anymore. Then you have to take it out, and now you have some super radioactive graphite that you need to get rid of. It's not impossible, but it's another step and an additional cost. First, you have to pay for that super expensive nuclear grade graphite, and then afterwards you also have to pay to get rid of it in some way. But if you can use heavy water, that heavy water can be reused again and again for hundreds of years. So it's not consumed and it's not damaged by the reactor. So it's a much better investment. There's a little bit of an investment up front in buying the heavy water, but then you can use it for such a long time and it doesn't degrade. But of course, then your problem is that we don't want to have that heavy water under pressure because we don't like things under pressure. So we have to have heavy water in the core at, say, 50 degrees centigrade, right next to pipes that are full of molten salt at 700 degrees. So there will be some thermal transfer from the hot pipes of salt over to the water. But actually, when we started to do the engineering or the math and the simulations, it turns out that the majority of the heat that goes into the heavy water is not from thermal convection. It's from the neutrons that the heavy water needs to slow down. So actually, that would happen anyway. So even if it was at high temperature. So the majority of the heat that goes into the heavy water comes from the neutrons, and then you get some from the gammas, and then finally you get some heat from the molten salt. Normal heat radiation. But the way we've constructed is that we have two barriers between the hot salt and the water. And it's made in a way where we pump the water into the core all the time, and then it runs out and we cool it down and pump it back in. So if the pump stops running, then the water will automatically drain out of the core quite quickly. And actually, it's the same with the salt. The salt is also pumped into the core, and if the pump stops, the salt will automatically drain out of the core. So that's a very simple way of, some of the other people who are working with molten salt reactors, they use a freeze plug, but we don't need that because, as soon as a freeze plug works in a way where if you cut the electricity to the cooler, then the freeze plug will heat up and melt and it will dump the salt. But in our case, as soon as you cut the power to the pump, the salt will dump out right away. And it only takes a few seconds. It's much quicker than having to melt a freeze plug. And we believe that it's also a more reliable method. Anyway, so that was a little bit of some of the highlights or introduction to how we have made the reactor design. I want to say one more thing about the sort of the way we think about these reactors. So we, of course, from the very beginning, we want to manufacture these on assembly lines, so sort of mass production. We want to put everything inside a box and then seal that box shut at the factory. And then when it arrives at the site where it's going to sit inside a nuclear or power plant, then we're not supposed to make any modifications to it there. The only thing is that we need to load the fuel. And that can, of course, it's a molten salt, so that can be done through pipes. So basically just load the fuel from another container into the reactor, basically the dump tank inside the reactor while it's molten. And then you shut that pipe. Once it's loaded, you shut that pipe, for example, by welding the end tight. There are some other mechanisms, but that's sort of the simple explanation. And then you can start up the reactor. And what comes out of the reactor is hot salt that goes to heat exchangers and generate electricity and comes back cold again. And then we heat it up one more time. But the salt that goes out of the reactor is, of course, not radioactive. So now we have all the radioactive components inside a sealed box. And that box is roughly the size of a 40-foot shipping container. So it fits on the back of on a standard truck. So it's really easy to move around. And once you can sort of finalize everything at the factory, you can ensure the quality, and you don't have to rely on educating people in whatever country and make sure that they assemble it exactly correctly. You can do all your quality control at the factory where the experts are working on it. So it's a very different way of constructing nuclear power plants than what we're used to. And then the next thing I want to say is that we want to have a business model where we do not sell those reactors. We actually build, own, and operate the reactor, and then we sell the heat that comes out of them, and we sell that on energy as a service contracts. So the power plant utility, or the company who operates the power plant, they don't need to worry about anything nuclear, because we take care of all that. We take care of the fuel supply, we take care of the licensing. They only need to take care of running the power plant. And usually those companies, they are used to running coal-fired power plants and gas-fired power plants. So they feel confident about that because they've done that for many, many years, and they don't need to learn about this new nuclear technology, molten reactors, what is that, and train their staff and take risk and all that stuff. So we don't only bring a new type of reactor design to the market, we also bring a new business model to the nuclear industry.
Yeah, I mean, the only place that I know that is going to operate in a similar way is the new plant that is being built in Turkey. Similar idea, selling the electricity by Rosatom without the need to provide the huge stuff that nuclear normally needs. So what I imagine is that since the design that you have is a burner, it's in your interest to be located with your reactor somewhere close to the actual waste supplier, we could say. So I can imagine that you are looking at the countries that are already nuclearized, that have some reactors that could provide the waste for you to manufacture the fuel for your reactor. Am I right?
Yeah, that's partly correct. It's true that we are definitely focused on starting the first reactors on this long-living isocyanates from spent nuclear fuel, and there's sort of right now 31 countries that have commercial nuclear power, and therefore they also have spent nuclear fuel. So you're right; those countries would be sort of a first choice. But for example, in Europe, it has happened many times that people transport spent nuclear fuel from one country to the other. So I mean, it's not that it's impossible. We've also seen Japan transport spent nuclear fuel to France and so on. So I mean, it has been done many times before, and maybe in a little bit more distant future, we could imagine that some of those countries who have spent nuclear fuel today, we would reprocess that spent nuclear fuel in their country, and then take these parts that we need as a Kickstarter fuel for our reactor. Then we would be allowed to transport that, of course, under heavy surveillance, but transport that to the site in another country where we're going to start the reactor. I do think that will be possible, maybe not from day one, but a little bit down the road. And that's, of course, because some of the countries who need the most energy in the future are not the ones that have a lot of spent nuclear fuel on their hands. So I think it will make sense for the world, if we want to see this green transition, that we allow this to happen. And like I said, it's already happening today. For example, Denmark, like you said, there's a law against nuclear. We do not have any commercial nuclear power plants here, but still, I know that they are transporting uranium through Denmark from the Netherlands to Sweden on a regular basis. I've seen those trucks every now and then. So I mean, that happens. So yeah, I assume we can do the same.
I can see that you are you're planning to provide many services, not only in the design of the reactor, but also operating, cooperating with utilities, and now we're talking about the fuel. Do you team up with other companies who can take over part of this workload, or as Copenhagen Atomics, you plan to provide everything under this one shield as one team to provide all this complex set of services for the plant?
Definitely for the fuel recycling. I mean, taking spent nuclear fuel assemblies and turning them into fuel for molten reactors and storing the fission products, we will definitely partner with other companies. But I'm sure also with the installation of the nuclear power plants in these big buildings where you have the steam turbines and generators and all that, of course, we will also partner with companies who are used to building those and operating those. And whether it's new plants being built or it's existing coal-fired power plants being refitted, we will do that in close collaboration with those type of companies. But also, I mean, we need lots of parts for our reactor. We already have more than 500 suppliers even today. And I imagine that we have even more suppliers in the future. So that whole supply chain is also part of the whole system that needs to be in place before this can happen. But of course, most of those suppliers are suppliers of parts for pumps and valves and heat exchangers and so on. So it's companies who already have business in those areas. But also what we're doing right now, we have done a huge amount of testing of components that are going to go into our first reactor. That's actually one of our claims to fame, is that we've already built those components for the first reactor, and we already tested those for more than a year, some of them for several years. At the moment, we have done more than 20 years of test time in our factory of all these different components. And we will continue to scale up our testing, because if you want to build molten reactors on an assembly line, you better make sure that all the components work perfectly. So there's lots of testing going on, and I believe that Copenhagen Atomics have done more tests on components for molten reactors than all the other startups around the world combined. And as we are ramping this up heavily right now, I hope that we can continue to take the leadership in that area. But of course, we are very interested in seeing nuclear energy having a sort of a rebirth or a revolution again, and get back in the marketplace. And therefore, you know, I'm pretty sure that even if we're very successful, Copenhagen Atomics could never supply all those millions of nuclear reactors that I talked about in the beginning. So we do want to have competitors, because I think the chance of each one of those 20 startup companies that are there now, the chance of those surviving is better if several of the companies are successful. So it's actually in our interest to see many of the other companies succeed. And therefore, we're also very interested in working with them and helping them. So one of the things we do is we manufacture a lot of these salts that are needed in a very clean type of salt that minimize your corrosion. And we are selling those salts to some of the, you could say, competitors or colleagues. And we're also selling those salts to universities and national labs. So because we needed a lot of salt ourselves to do our own testing, we ended up setting up quite a large salt production. And I think we will be one of the key suppliers for these salt for many of the other companies in the future. And not only that, we also supply some of the test equipment. For example, we have what we call a molten salt loop, which is basically just a setup where you can test components, pumps and valves and so on. And we've already sold a number of those to competitors and universities and so on, who also use them for testing. And this, I think it's important for us as an industry to work together to make sure that we actually can get nuclear back in business. And we want to support that as much as we can.
Mm. Yeah, that's it. On one side, we are talking a lot about the whole industry is responsible if one company fails in something, but it also works the other way around. The whole industry experiences a victory if one company delivers something new, arrives to some innovation. So I can see that this is what you're seeing here in the startup world that is needed and that should be pursued. One success of one company can drive the others to be more successful as well. Yeah. Would you go as far as saying that the innovations and inventions in this field should be, let's say, open source or part of like scientific heritage? Or are you rather going towards, okay, let's patent everything because this is my success that I invented?
I mean, we have patented some stuff and we've made some of our software and some of our hardware open source. So we are sort of doing both. I think we are one of the more open source companies. Some of the other companies are very aggressive in taking lots of patents. And I think it's also, to some extent, that is the driver of that is the investors. So the investors say, if I'm going to put my money in that company, you better get some patents. And so it's a sort of yeah, it's there's some great things about open source, but there's also good things about getting investments and having patents. And I think if somebody invented something really unique, I think it's fair that they can patent it and sort of keep those right for 20 years or whatever. And then of course the other companies, they can license those rights if they want to use the same invention. And I do hope that we as a nuclear industry do not start to fight each other over patents. That would be a waste of money because the only ones who win from those fights are the lawyers. So it's much better if we can sort of find ways to license things to each other if needed. Right now, I don't think we need any licenses from the other companies, but you know, it might happen in the future. And I do believe strongly in open source. If you make something that can be used not only in the nuclear industry, but maybe also in other industries, I think you should open source that if at all possible, because that helps everybody around the world. And I've used lots of open source, both hardware and software in the past. And let's be honest, I mean, if we look back in the world and how things were developed, cars, airplanes, everything, I mean, engineers, they borrow ideas from each other and they sort of look at what other people did and they try to improve it. So the whole way of sort of sharing design, that helps everybody. And if those who share the design, if they even make it so easy as to share their drawings and the software as a source code and so on, I mean, it just make that whole cycle of improving things faster. And I think that benefits everyone.
You're talking about crossing the industries. Do you think that the startups that you had in the past that were not necessarily related to nuclear, is this experience able to help you in the current endeavor that you have? Or is nuclear a totally different world that does not really have anything to do with the IT world?
No, what I learned in the past from the other jobs I had and other startups that I was part of, it's definitely very, very important experience. And I think every engineer, they learn stuff where they work and they bring that knowledge to their next job. I've had the great fortune to work for some very exciting cutting edge technology companies. So of course I had an opportunity to learn lots of things that I use today. I learned to weld, TIG welding like 20 some odd years ago. And I'm still using that every now and then when we are in the workshop and we're setting up experiments and many other things like that. And also the important thing is not only what you have learned, but it's also the people you know. And for this company, I've hired some of the best people that I've worked with over the years in other companies, because you know, if you get to know a guy or a girl and they are really clever and good at what they're doing, you know, that's really valuable. And of course, we would like to work with them again because they're nice to work with and they have great skills. And of course, in a nuclear company like ourselves, we need lots of skills. We need mechanical engineers, we need software engineers, we need electronics engineers, we need nuclear engineers and people who are good at simulations, whether it's there's many different types of simulations, not only sort of criticality simulations, but so we have a whole team of people doing simulations, and that's similar to what you do in other companies as well.
Amazing. And so looking at the close future for the startups like Copenhagen Atomics and other startups that are working as hard as you to achieve success in the next generation of reactors, what do you think would need to happen in the politics, in maybe humans' minds, to help you to accelerate this process, or at least not to slow it down in the coming years?
Yeah, there's an important community of people who are building stuff, and that's like what we do and other companies as well. That is very important. We need to have that, but it's also important to have people around that emerging industry to support the industry and explain what it is we're doing. And we have a lot of people who are sort of fans of what we're doing or really like what we do, and they communicate what we do to their colleagues and friends and family and so on. And I've even had people who are sort of, we have a number of, we have more than 1,000 small investors. I've had some of them come to me and say, can I borrow some of the slides from your slide deck? Because I would really like to do a talk about this at my whatever workplace or somewhere. And I think that's really helpful when thousands of people go out there and talk about what nuclear can do for society, because I think that's more trustworthy than if some corporate thing does it, or like even if a government try to push this down your throat. I think it's much more believable when the guy you worked with for 20 years, he's actually spending his time to try to explain to you, I've learned about this. This is how it works. You know, this is something we should look at as a society. And it's not enough if just one guy does that. But I believe that in 3, 4, 5 years from now, we will have 100,000 people around the world trying to communicate about these new type of small modular reactors and these new type of reactor designs that are much better than what we had in the old days. And I really believe that is what is in the end going to change the faith of nuclear and get it back, get trust back into society. There will always be some people who are against it and who are afraid of it. But I mean, I do believe that we will, within the next 5 years, I do believe in many countries we will reach more than 50% of the population who are in favor of nuclear and want to build more of it. And of course, the green transition is also part of that. So I see a great future for nuclear companies, and especially ours, because I think we are in a great position to scale up this technology.
So what should I wish to Copenhagen Atomics for the coming years?
I think you should cross your fingers that we will be allowed to start our first test reactor by 2025, because that's our next really big milestone, is to have the first test reactor online and operating by 2025. And there's still a number of technical hurdles and approvals and things that needs to happen for that. And I think, again, that would be a big step, at least for us. I mean, there's not many startup companies around the world that has managed to build nuclear reactors and get approval to start them. And I hope that in the next 10 years, we will see, I don't know, 4, 5, 6 companies do that. And I think that would be great.
Amazing. This is exactly what I want to wish you then. Thank you very much for a talk. It was amazing to hear you, your opinions, and I wish you all the best for the future.
Thank you.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.